What's Gucci, everybody? In this tutorial I want to talk about heaps. Heaps is a nice data structure where you're able to do a nice sorting algorithm with it called a heap sort, obviously, to go along with the heap, and able to preserve either the minimum or maximum of an element. And without further ado, let me show you guys an example. So a heap can be visualized as a tree. So a tree, again, is a couple of nodes, and a heap can be especially visualized as a binary tree. Now, a binary tree, oops, did I spell that wrong? Yeah, I did. A binary tree, meaning that it can have a maximum of 2 nodes. So let's say, in trees, this is the parent, and the parent can have children, obviously, and the children can then have 2 more children, can only have 2 children, and then they are parents too. So with respect to this node, this is so let me number these nodes 0, 1, and 2. With respect to 1, 0 is the parent of node 1, and 2 is also the child of node 0. And if I gave node 1 a child of 3 and another child of 4, we could say that 1 is the parent of node 3. Now, this is pretty important. I also like to refer to the first node in the heap or in the tree as the root. It also is a parent, but it also is referred to as the root if it's the first tree that starts the heap. Now, heaps can be visualized as arrays, which I want to show you at the end, but they are implemented with arrays, as I may say, but they are visualized as trees that cannot have more than 2 children. So let me just show you let me just put an example. So let's say I have an array that is 4, 1, 3, 16, actually let's put it 2, 16, 9, 10, 14, dang it, 14, 8, and 7. And I want to put all of these elements into a heap. Okay, so what I'm going to do here is heaps preserve order. So I'm going to show you how a heap does that. So what we want to do is we want to just start at the beginning of the array and add it to the heap. So I'm going to make 4 the grandparent, the root node. So I'm going to refer to 4 as node 0, and you'll see why at the end, because since array started 0, heaps also can be referred to as having a 0 position. So this will be the root. And now I'm going to add 1. And how heaps work is that it basically, you always want to try to fill it out from left to right. So after I fill out the root, I want to fill out this position, and then I want to fill out this position, and then I want to go to the next row, and I want to fill out the leftmost child of the leftmost parent, and then I want to fill out the right child of the leftmost parent, and I want to keep going from left to right and fill out that one, and that node, and fill out this node, and 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 try to complete the rows of the heap before I move on. So as you can see now, I'm going to add 1, and this is a max heap. So as we will see, the max value in this array will be preserved at the root of the node by the rules of the heap. So I'm going to add 1, and 1 is going to be added there. And then I'm going to add 3. And since 1 and 3 are less than 4, this is okay, because what I want to do is I want to check that each of them are less than their indicated value, or else I would swap them, which we'll get to in a second. So now I've added 1 and 3. My next number is 2, and I'm going to want to add 2 here. And as you can see, since this is a max heap, I want all the numbers on the top next to the root to be bigger than the nodes on the bottom. And as you can see, 2 is bigger than 1. So that violates this principle. And what we want to do here is that we want to insert 2 into the most current position that it can be inserted to, and then we're going to swap it up until it fits the rules of a max heap. So until its children are less than it, and it is not greater than any of its parents. So we're going to swap 2 and 1, put 2 here, and I'm going to put 1 here. So as you can see, now the heap is preserved and we can move on. So now after adding 2, we're going to add 16. And as you can see, 16 is going to trickle off the tree. So 16 is greater than 2, so they're going to flip. Put 16 here, I'm going to switch 2 here. And I don't stop here because I now check, is the parent greater than where 16 is now? And the answer is false. The parent is not. So I swap them again. I put 4 and 16, and now 16 is as you can see, we know 16 is the maximum value of the heap. So I switch 4, and now I'm going to put 9 in. So I'm going to put 9 right here, and I see that 9 is greater than 3, so I swap them. And there you go. And now I'm going to insert 10. And I'm going to do a nice 10 here. And I'm going to swap 10 and 9, even though they're close, but still 10 is greater. And I'm going to swap 9. And again, I would check, is 10 greater than 16? No, it's not, so I leave that. And now I'm going to do 14 here. And 14 is greater than 1, so I'm going to swap them. And 14 is greater than 4, so I'm going to swap them. And what else do I have left? So I have 8 and 7 left. And again, 14 is not greater than 16, so I leave that there. I'm going to put an 8 in. And I'm going to swap 8 with 4. So 8 with 4. And 8 is not greater than 14, so I leave it like that. And let's see, now I have a 7, so I'm going to put a 7 here. And let's put a 7. And 7 is greater than 2, so I'm going to swap those. Sorry. And there you go. I've added all the current elements that I said I would add, up to 7. So now what you see is that this heap is totally obeys the rules where each parent is greater than both of its children or just one of its children. It's possible for a node to have 0, 1, or 2, only 2 children. As you can see, 7 only has 1 child, and 3 and 9 do not have any childs because there are not enough elements to fill up the last row completely. And that's okay. That probably will happen in most of the cases. So as you can see, 16 is the biggest element, and then the second and third elements are 14 and 10, and 8, 7, 3, and 9 are the 4th, 5th, 6th, and 7th biggest elements. And as you can see, they are not ordered in any way. They are just descending from the parent node, which is bigger than them, and that's okay. There is some order in a heap, but there is not that much order. But as you can see, they're kept well, and that is okay. Now I want to add in one more thing, is that you can also represent a heap within an array. So as you can see, I started this at 0. If I gave these positions 1, 2, 3, 4, 5, 6, 7, 8, 9, and we'll call this 10, they can be represented in an array. And let me show you here. So if I have an array of 16, 14, 10, 8, and 7, and I could fill them all up, but I'll just leave it like that for any case. We'll notice, I want to just point some things out. We'll notice that, let me just number these, 0, 1, 2, 3, and 4, that the left node, if I want to find the left value of something, it's 2 to its index plus 1. So if I want to find the left child of a node, I know what position it's at in the array. And if I want to find the right child of something in the array, it's right equals 2n plus 2. It's just 1 over. So for instance, if I want to find the child of 16 by just looking at this array and not having a heap, I would plug in 2 to n plus 1. So n is the index. So 2 times 0 plus 1 is 1. So index of 1, 14 is a child of that. And same thing for right. 2 times 0 plus 2 is just 2. The index of 2 is the index of 10. Now, as you can see, this formula really helps if the tree is much bigger, and say I wanted to find the left and right, wanted to know the left and right indexes of position 4, which would be 2 times 4 plus 1, which would be 9, and 2 times 4 plus 2, which would be 10. So you could easily look that up. And also, if I have a child and I want to know what the parent is, what I can follow a formula where I do n minus 1 divided by 2, and what also to the floor. So for instance, basically what the floor function means is you round down. So what I'm going to do, let's say I have 6. I want to know the position. Oh, well, let me choose 4. So I'm going to take, want to know the parent of the node at index 4, which is 7. I'm going to take n, the index of 4, minus 1, which is 3, divided by 2. Now that's 1.5, but the floor function rounds down, so 1.5 rounded down would be 1. So the parent of 7 is 14, and as you can see at this illustration, it is indeed 7, and it always will follow that formula. So those formulas always apply, and remember that you want to start, if you're numbering your root, you wanted to make it start at 0 just like an array does, so it fits these rules, because these account for the index starting at 0 and not at 1 or -1 or any other number. Thank you guys. I hope you enjoyed this tutorial, and have a great day.